scientific spacecraft and instruments that are on there. So this is not something that's small. When you go in the field as I'm a trained geologist, and when you go in the field as a geologist, you have your eyeballs and you might have some other measurements that you will take in the field. It's different than studying the geologic materials and landforms and processes remotely where we can't go up there. You know, geologists like to stick their tongue on things, rocks. And so this is not something that we can do obviously on other planets. We can't get right up there with our nose to the outcrop. So we have to derive things a little bit separately, but we have a lot of different things that we can use, a lot of tools in the toolbox. And this is a blessing and kind of a curse at the same time. So the Geo-Renaissance, the spacecraft data alone is giving us a lot of good information, things that we would not have been able to do 20 years ago. So observations, this is just kind of a take from different kinds of instruments and different kinds of spacecraft. So gamma ray and neutron spectrometer data. We have radar data, high resolution visible wavelength, infrared data, carbon bearing gas data, so atmospheric data. Laser altimetry has really been a big boon for us to be able to couple topography with visible range spacecraft images. And so this is really a huge amount of data that we deal with and that we're trying to squeeze as much information out of to make the case for geologic settings on different planets. And along with that, we also have spatial resolution and the variance in spatial resolution and how that goes along with the scale of geologic map that we're making. So for example, we often have people that are asking to make maps through the USGS. We're one publication house. Other people can publish them at a journal article, but the USGS is kind of standardizing these maps and using standard processes to make kind of larger benchmark product. But resolution is really key for the scale that you're trying to map at. Somebody that's mapping globally on Mars is not going to use high-rise resolution, which is 1/4 meter per pixel. So these two things kind of go hand in hand. And primary data sets can range for different bodies from sub-meter to kilometer kind of pixel. That's the kind of space that we're working with. And then also derivative data products. We're getting down to tens of centimeters for certain kinds of spacecraft data and on certain bodies. And so we're really combining all these things together. And more data for geologic mapping is not necessarily a good thing. When we are asking people what kind of data they want, we learn some lessons. Before, we used to have kind of a checklist where we'd say, what data do you want for Mars map? And we had a list of data on there, and you can guess what would happen is that people would check every single box. And that's just not possible. Especially, it might have been possible when we had Viking data only, and then early days of Global Surveyor, where the data was limited. But now we have just too much data, and so people have to be very specific and strategic in what they choose to make geologic maps. Geo-Renaissance, speaking of the way it was done before, right? So now we have data that we can kind of access almost right off the cuff after some processing. But back in the day, and it wasn't all that long ago, we're talking about 50 years or so, that the data was actually translated by airbrushing. So these are folks at the USGS that were actually airbrushing and making a replication of the data. So a lot of the data was stitched together and then it was airbrushed, and the airbrush bases are what the early lunar maps were based on, and even some of the Mars maps as well. So it's interesting. So just translation alone, you're going to lose some of the information, and then deciphering what those images and those features are and how prominent they might be based on how somebody actually artistically rendered those things. So this is where we're coming from. So we've come a long way already, and I think we have a long way to go. What is it going to look like 50 years from now based on what we're doing? They'll probably be showing pictures of us doing the things that we're doing right now in some kind of crazy color. So it'll look like this and kind of, older, interesting. Data management is a big issue, obviously. So with the range of data set and the range of spatial resolutions, we have a ton to lean on, but that only works if they're sitting together some way. So on the left-hand side, we show all of our data. This is for Mars. So we have our visible images, and then you have ortho images, topography that's coming from that. Thermal data, daytime and nighttime. It could be 8-bit just as a qualitative representation, or you can have a quantitative representation of that. And then you have mineralogy. So all these things are there and are available to us, but it's a matter of how we can put them together and what they are useful for, how useful they are for geologic mapping. GIS, and so different platforms of GIS where we can integrate all of this information together. And this is something that's been dealt with for a long time on the Earth side, especially with city planning, and this is something that's newer for planetary folks. It's certainly come up the curve over the past 10, 15 years, but it's something that still people are struggling with, is integrating all this data together and the data standards that tie things together without having to massage the data into place, which is what all of us probably deal with quite a bit, is getting everything to line up. And then you also have data portals. You can access data and get it a lot of different ways. And that's sometimes really confusing because we don't know what the quality of data is that's coming from certain places or how much is replicated. So these are three kind of big obstacles. They're really good. The data is good, GIS is good, and the data portals are good. But if they don't work together and they're not addressing what the needs of the community are, then we have a big problem. So there's a big hurdle with just getting the data and getting to the place where you can actually start to do something with it. In our case, it's geologic mapping and defining units. So planetary science, along with many other disciplines or large-scale disciplines, terrestrial science, anything like that, is all based on lots of different facets. You know, computer science and chemistry, geology, geography, landscape of evolution and the shape of landscapes. Mathematics is obvious in there, engineering, physics, and these are separated here just to show the difference between everything, but it's obviously a Venn diagram. Everything is overlapping. And this is great, but it also makes it so that we have to be more knowledgeable in planetary science than maybe other folks are that are not having to deal with many other things. Every discipline has their complications, and planetary science is it's no different. It's just that we are leaning on all of these different kinds of things because we can't get up on the rock surfaces. Planetary geologists have to kind of leverage these other data sets that are out there. That doesn't make us special. It's just an acknowledgement that we are leaning on lots of sub-disciplines to get our work done. So planetary science and planetary geology tends to be more nuanced, and we have a long-term evolutionary view of the geology of our solar system. It puts things in context. So Apollo 11 observations, it puts those into a broader context. The things that are seen locally can then be placed into a bigger context. Mars' history of liquid water and identifying deltas and lakes. And the center view is Jezero Crater, where a lander will be landing hopefully in mid-February. And Charon's equatorial tectonic belt is potentially indicative of subsurface water. So we are evolving these views, and I work a lot with Mars geology, and even the time period that I've been working on this for 15 or 20 years, you know, things have changed quite a bit, and it's interesting to watch certain perspectives fall into favor, and then they fall out of favor as we gain new information and new studies are accomplished. And that's often tied to the kind of data that we're getting. You know, when it wasn't very long ago before HiRISE when we were looking at mock images and thinking that it was just the greatest thing because we could see so much. And then that quickly gets supplanted by HiRISE images. And that doesn't mean that the data goes away. We certainly should use all the observations that we have, but we form new hypotheses based on the allowable observations that are there. So for the USGS as being kind of the only place in the world right now that is publishing standardized geologic maps, and we'll talk a little bit about standardized versus non-standardized. And we started this in 1960 with Shoemaker and looking at the lunar surface. And then that was a Mason and Hackberry kind of near side lunar geology. So these are the first kind of planetary geologic maps that was trying to use a terrestrial standard to identify different unique geologic and stratigraphic units on other bodies. And the whole goal here was, you know, can this process apply? Can the process of identifying geologic units apply like it on other bodies like it does on Earth? And it turns out that it does, as long as it's based on consistent observation and the interpretations are separated specifically from the observations. We can't link things together on non-terrestrial bodies like we can on the Earth, just because we can't be up there and looking at the materials. So far, NASA and other institutions around the world have dumped a lot of money into resolving the geology, and that's through geologic mapping as well as also topical sciences. The geology is not only done, deciphering the geology of planetary bodies is not only done from geologic mapping, it's also done by topical studies. But I would argue that a lot of people are mapping even if they don't think that they're mapping. So there's lots of sketches that have been made on the back of napkins and on legal pads that are effectively creating geologic maps. And I think that, in my opinion, the crux of a lot of the investigations that we do and trying to resolve the geology and the evolution of some of these solid surface bodies in the solar system is contingent upon accurate geologic mapping. So I would argue that geologic map then spans all these different kind of facets of planetary science, and it is leaning on a lot of these different ones. I was speaking to somebody before is that geologists are geologists, but then also data scientists at this point, just because we have to use a lot of data, and that's very specific to planetary science, but also terrestrial scientists use a lot of remotely observed data. And so we have to couple those two things together, and you don't always separate, a scientist or a planetary scientist and a geologist from a data scientist. Our group at the USGS that's working with publishing geologic maps on behalf of NASA as USGS Scientific Investigation Map Series products, we have a group of folks, and they span the range from pure geologists all the way to pure data scientists, and that's the way it should work. We are fortunate because we do have the space to have those people, but there's a lot of people that are operating kind of alone or in couples, and they don't necessarily have the ability to have enough people to help them with the data analysis part, which is why it's incumbent upon the community to be able to make the data available to the extent possible in a way that is very useful for people that might not have that skill set. So geologic mapping is a critical, but not the only critical unifying platform that supports planetary science and exploration. We're not pretending that geologic map is the end all be all, but I do think that it holds an important role in coalescing the observations and putting those observations into a context at multiple scales. So terrestrial versus non-terrestrial maps, we get this a lot. And so not to insult anybody's intelligence here, but what exactly, we often talk about maps and geologic maps, what does that mean? And it's just a chart that displays bulk geologic observations, and here observations is highlighted. It's intended to visually convey the formative history of a particular area. So in essence, it is context, right? It's consistently recognizable and traceable units across the landscape. So those key words, consistently recognizable and traceable, we have to be able to identify something that I identify and describe should be used by somebody else to be able to identify and describe those same things. If they can't find what I'm finding, then there's a problem with the way that this has been observed and documented. We want to describe thoroughly and objectively what we see on that landscape so others can recognize and trace those same things and then verify the presence. So you don't have a lot of confidence in something if I draw a bunch of polygons on a body and then somebody else takes it and they can't see what I'm tracing, then that doesn't help anybody at all. And if you can't verify the presence and identify what another person is seeing, it's not helpful. So it has to be repeatable. You have to be able to see it, and it has to be repeatable and something that's useful. So a geologic map, the way that we see it, is minimally consisting of the map itself, as well as the key, the symbol key, or the explanation of map symbols, the EOMs. The description of map units, we call it DOMU, or the correlation of map units, which is the bars that are correlating units across space and time. And so those four things represent the map. So the map alone is not going to do anything for you unless you have a key, and the key is not going to do anything for you if you don't know how those features that are being mapped are fitting together in space and time. And so they all sit with one another. And what's interesting about preparing geologic maps, and we're dealing with this a lot lately, is that when you submit a map, it has all these different components with it. So if an editor comes back when it goes through technical review and changes one thing, so the unit name, for example, then it's going to impact every single thing that's in that map package. So it is very tedious to do, and we have to impress upon our mappers and reviewers and the community users how integral these pieces are and how they tie together to convey the information that we're trying to convey. So as far as terrestrial units and non-terrestrial units, on the left-hand side here, we have an example of a terrestrial geologic unit that's been mapped and is very well known. It's the Permian Kaibab. It's a limestone unit that sits at the very top of the Grand Canyon. And so the way that's described on the geologic map, and this is actually paraphrasing because you can go touch and see this rock unit, you can describe it at macro scale as well as a micro scale. And in geologic maps that you'll see that are published by the USGS, they do. And so these unit descriptions can span, half a page to a page long, and that's a good thing. And it goes something like this, so lower Permian, that's the age of a unit when it was placed. Yellowish gray, light gray, silty, sandy, and gives all the different kind of chemical characteristics of it. Its grain size, its thickness, how that thickness might vary through space, and if it's tilting in any one way. So all these different things that can be described. So for non-terrestrial geologic units, obviously we can't say some of these things. We certainly can't say anything about grain size. The only thing we might be able to say is if something is eroding into blocks, or if it might have columns that are visible at a certain scale. So we do see columnar joints and columns that are, multi-meters across on Mars. Those things typically form in volcanic units where there's a lava flow or a welded kind of ash. So we can see those things, but we can certainly not see grain size unless you're up there on it. You're never going to see grain size remotely. That's just almost a fact. We can only see that when we're up close. So non-terrestrial unit descriptions go something like this. Hesperian age, that's its position in time. The age 3.8 giga Anna, that's based on impact craters and the density of impact craters and how they scale to lunar equivalents, for which we actually have absolute values. And we say plains forming deposits marked by sinuous ridges, anabranching ridges, irregular depressions, has a low dielectric constant if you know something about the radar properties, hundreds of meters thick if you see it in outcrop, or maybe the radar properties can give you that kind of indication. And then we have an interpretation that's separated from the observations of it. Water ice sheets, perhaps in place by cryovolcanism or atmospheric precipitation, covered by a thin ice-rich mantle. And so for our unit descriptions, we're actually separating things out. We have a definition, and then we have an interpretation. And those interpretations have to derive specifically from the observations that are made. And often, if you look at our maps, the observations are split into two different kind of categories. One is the definition, and one is additional characteristics. And the definition is based on the single most continuous data set that is being used to identify that unit. That's the base map, and that's how the definition is made. And then you have additional characteristics that's talking about how it might look locally if you have some high resolution images. And then from those two things together, you can derive an interpretation. So planetary geologic maps are typically more descriptive and less interpretive, right? And so interpretations must be hedged. We can't say definitively what something is. You can certainly move down that road, and we have in certain maps in the past that people want to say that this is a basalt, which is a volcanic rock, and it is erupted a certain way, and it means something about how it evolves in the mantle of a planet. So interpretations must be hedged, and alternatives need to be provided to make them useful. It needs to be based on the state of knowledge as we know it right now. We understand that there would be more data in the future, and we don't think that if we put a map together appropriately, the data that's accumulated in the future will not blow away the map. It might blow away interpretations of units, but it shouldn't blow away the units themselves. And that's what we've seen happen over and over again, even when we start comparing what we understand now about Mars from what we understood based on data acquired in the 1970s. We can't know everything without a contact, right? So we can't contact, meaning not geologic contact, but actual physical contact. If you don't go up to it and look at it, with your eyeballs or something that is equivalent to your eyeballs, you're not going to be able to understand what that thing is. So we have to do our best. So we either say we're not going to do anything at all, or we do the best that we can. And we are certainly going to choose the latter. We can do a lot remotely. We can, however, strategically blend data to convey observations. So that's that scientific, technical, and the interplay between the map. So all those three things kind of go together, and we can very strategically use and squeeze this data in order to give a representation of an objective representation of what we think the characteristic, the geologic characteristic of a particular body is. Data and data management is affording and is greater than the interpretation. So we can't do any of this without good data and without good data management. So standardized versus non-standardized. Those that strictly implement cartographic rules versus those that do not. And this doesn't mean good versus bad. And we always have to kind of describe this because we don't want to pretend like the USGS or anybody who's making a standardized map is better than somebody who's not. There are pros and cons for each. So apples and oranges, right? And I've used this particular picture a lot just because it seems like they're angry at each other and they don't want to be accepting or even acknowledging that the other one exists. And this is just not the way. The fact is that we're all basically apples. We're all one of the same thing. It's just that we're breaking down along different lines and we're useful for different things. You're not going to make an apple pie with a Golden Delicious apple because the Golden Delicious apple is just going to fall apart into schmutz. And so, hey, you want a Granny Smith? I don't know if that's true or not, I'm just guessing. But they're useful for different things and people tend to gravitate towards them based on what they want. And so we have terrestrial, non-terrestrial, and then non-standardized and standardized geologic maps. And they kind of break along these different boundaries. So geologic mapping specifically and how it relates to discovery, innovation, and application. So geologic maps result from and promote additional geologic investigation. So they are a higher order data product that also enables the generation of higher order data products, and they further investigation. And so if they're properly prepared, and that's an important part there too, is that we find that the most useful geologic maps are the ones that are prepared objectively and follow known procedures so that everybody understands the way these things have been prepared. And of course, there's wiggle room in there. And as long as it's described, there's a lot of leeway that people can have, but people need to understand how they are being prepared. The best examples that we find are probably for landing site analyses. And this is always done before an asset is sent to another planet. And certainly if that asset is organic, as being a human. So Apollo 17 on the left-hand side, these are the folks that are actually in place and up on the rock. And on the right-hand side, you have the proposed landing site for Apollo 17. So landing site analyses are always beneficial. So we had the Apollo 17 example, but you also have the Spirit example, and then now Mars 2020. And geologic mapping is one of the key pieces of information that helps place all of these topical science investigations in and around the landing site into a context. We're proud to just now release a map that was authored by Vivian Sun and Katie Stack at the Jet Propulsion Laboratory for Jezero Crater. This was done at 1 to 75,000 scale, and this was a quick turnaround map that was done not necessarily to help guide the rover, but help to place the rover observations into a broader context. It's great to have local observations from landed assets, but to make the most use of those, we need to be able to take those very specific observations and put them into a broader context. And so this scale of map that they selected and that we have now published and is now available online is supposed to be kind of one of these bridge scales that will enable comparison of the localized observations into an intermediate scale context that can then be kind of pushed out to a broader context and look at more of a regional to even hemispheric scale. So landing site analyses are great for geologic mapping and integrating data together and providing a context for observation. So innovation, what are we doing? How are we going to go from where we are now into the future, and what is that even going to look like? And so how do we make it be that in 20, 30, 40 years, people will be looking back on us like we were just looking back on this picture of people airbrushing the surface of planets? And I think that I love hard copy maps. I love these flat maps, but representing three-dimensional objects, which you have to only do with projections, on a hard copy map is really difficult. They become unwieldy at times. They are distorting certain features. You don't get the full range of what you're really seeing. It's a good context, but it's not the most perfect way to absorb this information. So map packages and layers of map material and an immersive world is probably the way we're going to go. We need to start looking at things a little bit differently and having not just kind of a flat map, but how can we really get into integrating the data and being able to look at data at different scales. And that's going to mean innovation in how to symbolize things, different scales, even machine learning, so that we can have a first pass by a machine do some geologic mapping for us, and then we can go and clean it up based on a human knowledge about how things are supposed to look and how they might be situated in space, that kind of spatial understanding about how things fit together. So promoting application. There's a fundamental science that geologic maps provide, and there's also the applied science. So fundamental science, because it's expanding our body of knowledge. The first thing that we do when we go to a place is to start to look at the geologic context. What are the units that are sitting there? How do they fit together in space and time? It promotes discovery and invention of different processes. We're right now trying to figure out how best to map impact craters, for example, on multiple bodies. And so we can invent the processes and test them out and see where they break down. We understand that there's just a lot that we don't know, and that fits into that fundamental science. So it's investigator driven, and it's a flexible timescale on the production of something that's for fundamental science. Applied science has a much more tight time constraint. And so it's client driven. It is, for example, it's for the mission, and it's something that was expedited and that we need to get really quickly. So it would be useful to not only the mission, but folks that are going to be looking at the data that's derived from the mission, and also, just the somebody from the public that wants to interact with this data and understand what's going on. So we obtain this for knowledge, obtain knowledge for practical application. That's technology advancement, apply what we already know versus something that we are learning for the first time. So like I said, client driven and turn around on a tight time scale. And for planetary geologic mapping, this has to do more with like landing zones and resources being lots of different things. Trafficability is kind of a resource. Solar is a resource. So anything that is going to help us land and also sustain our presence on a particular body. Habitability, past and presence, livable spaces. Where are the caves? If we need to find caves in order to persist on a particular body, then that's what we need to do. And how do they fit together, and how do they interact with geologic mapping? How can the maps help us identify these places? Like I said, hazards, and then eventually we'll get to a place where there's land use and even political boundaries on these bodies. And so all of this is going to be integrated together. All of this can be integrated into a geologic map cube and be used for applying the science. The next thing that's on the horizon for us is us as a community, not just us USGS, is Artemis moon missions. And so this will be something that's a rapid turnaround, that a lot of players will be involved in this, and selection of the landing site and what is done there. So this is kind of our first foray back onto the lunar surface, and we'll segue into further exploration of the moon, as well as further exploration of other bodies, including Mars. So this is our next big thing, and geologic mapping will play a role, as will sound data science and data management. So next steps is to kind of try to break, this is what I see, is to break the idea that maps are these flat products that are single topic, that are static scale. I'd like to see these go the way of the dodo. I think that it's important for us to start understanding that they do represent a snapshot, and they're not going to go away tomorrow. I mean, hopefully they won't, because then we're kind of out of a job, but we certainly need to be thinking down the road a little bit on how we can make something multi-scale and what that means, and how we can integrate data together to represent things at multiple scales. We need to continue to advocate for all styles of geologic maps, not just, so there's geologic maps, there's geomorphologic maps, there's superficial geology maps, there's bedrock maps, there's hazard maps. All these things together can represent basically a geologic map cube. We certainly need guidance from the community on what products are needed. So we can go investigate, Jim's favorite place on Mars, but is that really going to do anything for us in the long run? We need to identify the places that are the highest priority, both for fundamental science as well as for applied science. And we want to innovate the map process and the product. Like I said, geologic map cubes of data, that's going to be the way to go in the future, is integrating all the different kinds of maps and how they fit together. Augmented reality is something that's becoming a big thing pretty quickly, and how we can immerse ourselves into the observations and make further observations based on geologic mapping and topical science. And then we want to apply maps to the next phase of off-world exploration, identifying resources, hazards, and making wise and safe use of our national assets, including humans that will be venturing to these surfaces. So geologic mapping, and then this is the last slide. Geologic mapping provides context, and I love this picture just because I think that it is a snapshot. And so don't rely on one frame, is to expand your look a little bit. So even if you're looking at one little frame or one little location on the surface of Mars, it needs to be placed into a context. And that's the job of geologic mapping, is to help you back up a little bit and place those observations into a bigger context, so you understand a little bit more about the role that geology plays in surface evolution. So that's all I have. I'm happy to take any kind of questions or comments. And yeah, thanks for listening and letting us be a part of this today.